Okay, now recording. Share the screen. All right, I'm basically done with everything we need for the exam next Thursday. So I was going to show you maybe one more problem from 14.8. It's a little bit more complicated. Okay, and then at the end of class today, I'll give you a quiz on something like 14.8. Okay, so that means I'm going to get started with 15.1 and maybe even sneak in some of 15.2, but we'll see how far we go. Okay, so the calendar adjustment now. So on paper, I've got down here 14.8. I was only going to do one more problem with it, and then 15.1, and who knows, maybe some of 15.2. Okay, next Tuesday, the 16th. Okay, so second half of class, I will let you ask questions because again, we will not have a question and answer session on the 18th. We will just go straight to the exam. As you know, some of the problems are really long. So I was going to let you have the entire class period for the exam. Okay, so any questions would have to be brought up the 16th. So part of your homework, I guess, for the next class meeting, the 16th, is if you have any questions on this stuff, right? 14.1 to 14.8, then bring it up. Okay, but in the meantime, I'll get going with chapter 15 and see how we get along from there. Okay, so 15.1, maybe 15.2 by next Tuesday, but I'll dedicate the second hour for questions and answers. And if that stops, I may just keep going ahead and lecture some more, or depending on the time, we may just go ahead and end early and whatnot. Okay, and then, yeah, per my usual rules, after class on the 16th, next Tuesday, 16th, I will take homework anytime after class up until half an hour after the exam ends on Thursday, right? So if you already finished the homework and you want to submit it after class, I don't want it too early, so please don't submit it now. But after class, the day before an exam, you may start submitting the homework. So after class the 16th, you may start turning in the homework early if you wish. But otherwise, as usual, I'll start right away, put the exam on Canvas announcements. If anybody wants it projected, let me know, I can project it also. And you have the entire class period until 8:25. Then 8:25, I close the Zoom. You have 5 minutes to submit the exam by 8:30 and another half an hour, so 9 o'clock to submit the homework, okay? So that's the way that would work there, okay? All right. Right, so we'll go ahead and get started then. Okay, one last problem from 14.8 and then finish. So again, what do you want to put on your cheat sheet on page 976? Oh, no, I don't want that. Wrong page, sorry. 972, box 1. Gradient of f is equal to lambda gradient of g. Del f equals lambda del g. Okay, then you end up with a system of equations that we have to solve. Okay, so you end up with a list. There's a box there. I mean, do you want to put that on your cheat sheet? It's up to you, but the more you put down there, then the less you have for, you know, other stuff. Okay, so you evaluate the function value at all the points from the previous steps. The highest of those would be the maximum, and the lowest of those would be the minimum. Okay, so the last problem I was going to show you was 11 because that's a little bit unusual. Okay, f of x, y, z is x squared plus y squared plus z squared. X to the fourth plus y to the fourth plus z to the fourth is equal to 1. Okay. So at first glance, it seems fairly ordinary, like all the other ones I did last time. You know, last time I did a 2-dimensional version, 3-dimensional, and even a 4-dimensional version. Okay, but let's take a look at what's happening here. All right, so this is a 3-dimensional version. F of x, y, z is x squared plus y squared plus z squared, subject to x to the fourth plus y to the fourth plus z to the fourth equals 1. So this is my g. Okay, so I said del f, gradient of f equals lambda gradient of g. Okay, the derivatives are easy. So fx, fy, fz are 2x, 2y, 2z equals lambda 4x cubed, 4y cubed, 4z cubed. Very easy, right? Okay, so the x components have to match, which is that equals lambda times that. The y components have to match, so 2y equals lambda times that, and 2z has to be lambda times that. So we end up with these here. 2x equals 4x cubed lambda, 2y equals 4y cubed lambda, 2z equals 4z cubed lambda by symmetry. Okay. Now, one technique that we did for the other ones is in each case solve for lambda, and then I'll set them all equal to each other. Okay, but there's a little bit of a twist to that. Okay, to solve for lambda, I divide by 4x cubed, right? 2x equals 4x cubed. Similarly, lambda is 2y over 4y cubed. And similarly, lambda equals 2z over 4z cubed. Okay. The trouble with that is that assumes x, y, and z are not 0, right? So we have to account for the fact that one or more of these can be 0. Okay. So if x, y, and z are all not 0, okay, then I can set these equal. I can cancel an x, cancel a y, cancel a z, right? Basically, you have 1 over 2x squared equals 1 over 2y squared equals 1 over 2z squared, which says plus or minus x equals plus or minus y equals plus or minus z. Okay, but that's under the assumption that none of them are 0. Okay, if you look back over here, x is allowed to be 0, right? In fact, 0 works. It clearly works. Y equals 0 also works. Z equals 0 also works, right? So what I have to do is consider what happens if one or more of these is equal to 0. Okay, you see, how come I never did that for all the other ones? I didn't have to worry about it because it never occurred. Okay, that problem never showed up. But here, okay, so if x, y, and z are all non-zero, this is true, correct? Now, suppose only one variable is 0. Suppose x is 0. Okay, well then if the others are non-zero, they still have to be true, which means y and z are plus or minus each other equal, right? And likewise, maybe 2 of them are equal. So they all have to be considered. Okay. In a nutshell, I do have to consider what happens if all 3 of them are 0, which is actually not possible here, or 2 of them are 0, or 1 of them is 0, or none is 0. Okay, let's get this out of the way. All 3 of them are 0 is not possible, correct? If they're all 0, 0 plus 0 plus 0 equals 1, impossible. Fortunately, we have a lot of symmetry, right? You see x, y, and z are all functioning the same here and here. So when I apply the idea of let one of them be 0, I can pick any of them. The logic will apply for the others also. And I can let 2 of them be 0, but I cannot let 3 of them be 0, correct? All right, so here's the analysis that I did. Suppose 2 of the variables are 0. That's possible, right? Okay, one more time. Okay, all 3 of them cannot be 0. 2 of them can be 0. Okay. So if 2 of them are 0, let's say x and y are both 0, then I have z to the 4th equals 1. Z is plus or minus 1. Correct? Right? So one more time, 2 of them are 0. Let that be 0. So z to the 4th equals 1. Z is plus or minus 1. So f of x, y, z would be 1. 0, 0. Either plus or minus 1 would give me 1. Okay. So that's the case where 2 variables are 0 and the other is plus or minus 1. It could be x is plus or minus 1, 0, 0. It could be 0 plus or minus 1, 0. They're all equivalent. Okay, next I consider one variable is 0 and the other 2 are not. One variable is 0, 2 are not. So let's say z equals 0. Okay, so imagine z is 0, but the others still have to be true. In other words, plus or minus x equals plus or minus y. Okay. So that will lead to x to the 4th plus y to the 4th is the same as x to the 4th plus x to the 4th equals 1. Okay, 2x to the 4th equals 1. X to the 4th plus y to the 4th equals 1. But if I have plus or minus x equals plus or minus y, that gives me 2x to the 4th equals 1. x to the fourth is a half. X is plus or minus the fourth root of a half. Likewise for y. Okay, plug those in. So if I plug in z is 0, plus or minus fourth root of a half, plus or minus fourth root of a half, the fourth root of a half squared is the square root of a half. Okay, one more time. If I have the fourth root of a half squared, multiply it by itself, you get square root of a half. So I have square root of a half plus the square root of a half plus 0. Clean up that algebra, it's radical 2. Okay, finally the case where none of them are 0. Okay, so one more time, I asked myself, what happens if all 3 are 0? Not possible. If 2 of them are 0, the other is plus or minus 1, function value is 1. How about 2 variables 0? Sorry, 1 variable is 0, the others have to be plus or minus each other. The function value is radical 2. And now how about all 3 of them are non-zero? In other words, I can divide by 4x cubed, divide by 4y cubed, divide by 4z cubed. Okay, that means plus or minus x equals plus or minus y equals plus or minus z. They're all equal. Okay, so if they're all equal, I can call this, or opposites. That would be x to the fourth plus x to the fourth plus x to the fourth. 3x to the fourth equals 1. X to the fourth is 1/3. So x is plus or minus fourth root of a third. Same for y, same for z. So they're all plus or minus fourth root of a third. If I square fourth root of a third, I get square root of a third. Okay, so you have square root of a third plus square root of a third plus square root of a third. Okay, that's 3 over radical 3, which is radical 3. Okay, so finally we have it. Square root of 3, 1.7. Square root of 2, 1.4. And we have 1. All right, so max, we have a tie between 8 possibilities. F of plus or minus fourth root of a third, plus or minus fourth root of a third, plus or minus fourth root of a third, which is radical 3. That's 8 possibilities, because either x or y can be positive or negative, y can be positive or negative, z can be positive or negative. So if you can run through them, you could have plus, 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 minus, plus, minus, plus, minus, plus, 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 minus, 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 plus, minus, 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 plus, and minus, minus, minus. You don't have to write them all down, but there's 8 possibilities. Trust me for that. And then the minimum was the case over here where 2 of the variables are 0 and the other is plus or minus 1. That leads to 6 possibilities. F of plus or minus 1, 0, 0, or f of 0 plus or minus 1, 0, or f of 0, 0 plus or minus 1. And the function value in those cases would be 1. Okay, so that's what we have for that one. So it's a little bit trickier, as you can see there. All right, and I am now officially done with 14.8, and indeed, I'm finished with all of chapter 14. Okay, so exam will cover up to here. I'm going to get started with chapter 15, but anything I say from here until next Thursday's test will not be covered on the exam. It'll be on the next exam, whatever that is. Okay, so I'll start 15.1. So chapter 15. Topic is multiple integrals. That's on page 987. Okay. So whenever we have the next exam, it'll be after the spring break, of course. So what do we have? We have 9 sections, and our last chapter will also have 9 sections. Okay. All right, multiple integrations. We're going to be doing a lot of things analogous to what happened in Calc 1 and Calc 2. So I'll be saying, think back what happened in Calc 1, think back to what happened in Calc 2, and then we just apply same thing to multiple integrals. Okay. So by way of introduction on page 988, okay, remember this kind of picture? Estimating the area under the curve, right? So here's a function trying to estimate the area between A and B. So we did Riemann sums. We chopped this up into so many pieces, right? In this case, it looks like 1, 2, 3, 4, 5, 6, 7, 8, 9. Chop it up into 9 equal pieces. Your delta x is, b minus a divided by n, or 9. Then you pick a representative point on each subinterval, right? You go straight up until you touch the graph, draw a rectangle, and go straight up, draw a rectangle. Now, these are all over the place. In Calc 1 and 2, you probably just did the left endpoint, right endpoint, and midpoint, right? But depending on your teacher, maybe you did the point that's 25% of the way over, or 75% of the way over. That one looks like in the middle. That one looks like the middle. This one looks like it's maybe, I don't know, 60% over, and that's 75% over. Theoretically, you pick any point. Okay. But most likely your teacher had you take left endpoints, right endpoints, and midpoints, right? To estimate the area under the curve. What's the analogy for us? Figure 2. Z as a function of x and y. So again, this is why we're letting z be up. We want z to be the height. Okay. So we want to estimate the volume over some region, just like from A to B, area under the curve. How about volume underneath a space figure, right? And right here, I want to estimate the volume right there. Okay. Here's the corresponding picture, page 989. So notice you have the normal x and y axis. You have a function over it. See all those dots? Those are representative points on each plot of land, as it were. That's sort of like over here, where you could pick the left endpoint, right endpoint, midpoint. That looks at the point that's maybe 10% of the way over and 75% of the way over. Okay, so the equivalent in multidimensional is this. Okay, so you have your delta x and delta y. Over here, it was only delta x, right? Delta x and delta y. So here's the plot of land, this rectangular region. Right now it's rectangular, but later on it doesn't have to be rectangular, which is nice. Okay, then you decide to chop this up into so many pieces and you have a delta x, right? Chop, 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 chop this way. And you also chop it up in the y direction, chop, chop, chop this way, and you have a delta y. So in this picture, okay, we divided x into, I don't know, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 regions. And in the y direction, we chop it up into 1, 2, 3, 4, 5, 6, 7 regions. Is that right? And all these dots are representative points. So the idea is you take these points, go straight up until you touch the graph. Okay, just like over here, right? Go straight up until you touch the graph. Look at figure 4. At the very bottom there, you take each of these points, go straight up, and you get a picture like figure 5. Right? Can you see that? At each little plot of land, you pick a representative point, all those points there, you go straight up until you touch the graph, and you get all these kind of like high-rise buildings here. Right? So your estimate for the volume would be the sum of the volumes of all of those high-rises. Just like your estimate for the area under the curve, right, is the area of this rectangle plus the area of this rectangle plus the area of this rectangle. Just add them all up for Riemann sum. So what's our estimate for the volume? Just take the volume of each box. There's 70 of them. Don't worry, I'm not going to make you do 70. Okay, but you would theoretically add them all up, and that's our estimate for the volume underneath the surface. Exact same thing. Now, you're not going to, in general, pick these. This is a theoretical thing, right? You could pick any point you want. Just like over here, technically you could pick any point in between, but what did you do in Calc 1 and Calc 2? Probably you just picked the left endpoint, right endpoint, and midpoint. here, can you guess the 5 most likely points that you would pick for any rectangle? Let's just focus on this rectangle. The same logic would apply to all of them. I can see 5 possible points to pick, right? Upper left, upper right, lower left, lower right, and midpoint. And that's exactly what you're going to do. So we're not going to pick, these funny ones here that are, 1/3 of the way over for X and halfway for Y, or 3/4 of the way over for X and 2/3 of the way for Y. We're not going to do those. Okay, you will pick either the upper left, upper right, lower left, lower right, or midpoint. Just like over here, you picked left endpoint, right endpoint, and midpoint, and you probably didn't bother with weird stuff like this, 10% of the way over or 75% of the way over, although technically there's nothing wrong with doing that. Okay. Okay, page 990. So we're going to be doing a double integral. Double integral over a region. R stands for region there. Okay, there's a very formal definition. We're not really going to use it, but just like for Calc 1, okay, M and N are both approaching infinity. You have the summation of these guys, delta A. What's delta A? Little change in area. What is delta A? It's dx dy or dy dx, a little change in y, little change in x. And by the way, now when I say dy dx, it isn't the derivative that looks like dy over dx, right? In Calc 1, when you saw dy over dx, we said dy dx. But here now when I say dy dx, it's not, it's going to be literally dy, and then next to it we'll say dx. Okay, and we'll see that. And we're also going to have dx dy. Yeah, here's some examples, right? Like number 7, dy dx. So now when I say dy dx, we're talking about integration. So we're probably not talking about the symbol that looks like dy over dx for derivative. We're focusing mostly on integration now. So now when I say dy dx, it's going to be this. And we could also say dx dy also, right? So we have delta A, which in the limit becomes dA. Okay. I wouldn't bother putting this on my cheat sheet because there's no homework problems involving it. Just a theoretical construct. Okay, you probably don't have to put this down either, but the volume is the integral, double integral over the region of f of x, y, dA. Okay, just like area is the integral for a to b of f of x dx. So the volume would be a double integral. You've got a delta x and a delta y, right? So x is going to go from one number to another number. Y is also going to go from something to something. Okay? And dA, and the dA is a tiny change in area. And we know that can be dx dy, or it can be dy dx, both directions. Okay. And yes, we could calculate Riemann sums. We're going to be doing some Riemann sums. Okay. Look at figure 6. Here's a picture which I can't draw, but it's z equals 16 minus x squared minus 2y squared. Okay, here's a picture of what it looks like. Estimate the volume. Okay, so they chop it up into 4 regions, 2 by 2, which obviously isn't very accurate. So I don't know, can you see those 4 high-rise rectangles there? So that one, that one, that one, that one. You would add them all up. And it looks like in the example, they picked the upper right corners of each rectangle, correct? Upper right, upper right, upper right, upper right. Go straight up, get the height, make my high rise. So this is probably not accurate, but as you might guess, as m and n, what are m and n? The number of pieces you're dividing x and y into, m and n, alphabetical. So m before n, so x before y. So m is for x, n is for y. So look at letter A, 4 by 4. Letter B, 8 by 8. 16 by 16. You can see the approximation gets much, much better the bigger m and n get. So the volume goes from 41.5 to 44.875 to 46.46875. which one do I think is the best approximation? C, right? Chop it up into 256 pieces, right? So we're just getting a Riemann sum here. All right, so we'll pick, left, upper left, upper right, lower right. We could pick a midpoint. Yeah, don't bother putting down that rule. You're just going to pick the point that's right in the middle, perhaps. Okay. Okay, on page 993, we have something called iterated integrals. So how do we actually do the integration? All right, so we're going to split it into two single integrals. So if you look at number 7, that's typically what we would do. Integral from a to b of the integral from c to d, f of xy, dy dx. Or you could switch it. You can do x first and then y. Like this, dx, dy. Just have to make sure that the limits correspond. Okay, so it works its way in. So the integral that's further to the right, so look at number 9. It says a, b on the inside, that's for x. And then c, d, that's for y. So it goes inside out. Okay, almost like order of operations. And those brackets are really suggestive, right? It's something inside something. And what's inside the integral is another integral. You're doing an integral of an integral. Right? So yeah, look at 8 and 9, contrast 8 and 9. So for 8, it looks like you have dy first. So it goes c to d, those are the limits for y. And then the outside, a to b for dx. And number 9, they reverse it. You get the same answer, but notice now you have the dx inside. A and b, those are the limits for x. That's reversed from number 8. And then c to d for dy. So I know it's not focused now, but okay. Whoops, this one. So c to d are for y and a to b for x. This means do y first. If you switch it around, okay, dx, x is from a to b, and y is still from c to d. So these are considered equivalent. Okay. It's just a matter of do you want to do x first or do you want to do y first, right? But in both cases, y goes from c to d, but here it's done first, here it's done last. Over here, you do x last, it's going from a to b, but on here, it's still a to b dx. Okay, so if you're going to switch them around, then the limits also have to be switched correspondingly. Okay, so when you have multiple integrals, you're going inside out. So the inside one gets done first, and then the outside one comes after that. Okay. All right. Page 994 is something called Fubini's theorem. I really don't think you have to write this down. Okay. But it just says if you switch the limits of integration, if you go dy dx or dx dy, you get the same thing. Fubini's theorem, page 994. I would suggest don't put it on your next. And again, this is the next cheat sheet, not on the test for this coming Thursday, but the one that's not for a while, not until after spring break. Okay, but again, please notice that the limits here, this says dy dx. So CD is for y, AB is for x. And if you switch it around, dx dy, now AB, that's going to be for x, and CD is for y. And that follows the rule over here. So these are going to be considered equivalent. So in other words, it doesn't matter if you do x first and then y, or if you do y and then x. And this is what they're trying to show you. I trace along the x direction first and then go y. This one you trace along the y direction first and then you go for x, but you're still going to end up with the same volume, obviously. Okay. And we'll look at some of those. Okay, so I think we're ready to start some stuff. So 15.1. So now when I say start building your cheat sheet, it's not for this next Thursday's test, it's for the test after that. So 1, 3, 15 to 41. Okay, so page 999, oh, 999. up to 1,000 almost. Okay, so there's 1, 3. I didn't have you do too many of these because they're really no fun to do. Okay, so just 1 and 3. And what else? 15 to 41. It's nicer. 15's at the bottom there, unfortunately. 15. And how high do we have to go up to? 41. Edge 1,000. Okay, hopefully you can see that. And more. 5. And up to what? 41 was it? Yeah, 41. Okay. Okay, so let's try some of these. Number 1 involves a Riemann sum, and so does number 3. Estimate the volume of the solid that lies below the surface z equals xy. Don't try to graph it. And above the rectangle R is such that x is between 0 and 6, y is between 0 and 4. Use a Riemann sum with m equals 3, n equals 2. So m is the number of pieces that you chop up x into. N is the number of pieces you chop up y into. Now in Calc 1, you only used n, right? So back in Calc 1, when you had pictures like this by analogy, right? Okay, let n be, I don't know, 5, 6, 10. That means chop it up into that many pieces. Okay. Now you're gonna have an m and an n. So m is 3, chop up the x into 3 pieces. So let's see, from 0 to 6, you go 0, 2, 4, 6. N is 2. That's for y, so 0 to y, so 0, 2, 4. So it looks like we got squares. Okay, A. Take the sample point to be the upper right corner of each square, upper right corner. And then B says use the midpoint rule to estimate the volume. Okay. So here's my picture. The function is x times y. There's a graph. We're not going to actually graph it. You need 3D software for that. But just imagine some heights. Like at the origin, the height is 0. And way over here, this is the point 6, 4. The height is 24, right? So it's way up here. Here it's 0. And you have other heights. Just imagine this function here that we're estimating. All right, part A says use the upper right hand corner of each square. So I take these 6, right? If you look at any one square, let's take, just look at that first square nearest the origin. This is the upper right. Or suppose I take, running out of, I look at that square, then the upper right is this one right over here, right? So these are the 6 upper right-hand corners of the square. Agreed? All right, so just like when you did base times height, here you take the base area. All the base areas are 4, are they not? 2 by 2. They're all 2 by 2s. That's just like when you were doing base times height for these, right? Base times height. All the bases were the same. It was delta x. Here, all the bases are delta A. Delta A. They're all 2 by 2, right? So 2 by 2 times the heights at these 6 right endpoints. So here they are. It's f of 2, 2, f of 4, 2, f of 6, 2, plus f of 2, 4, f of 4, 4, and f of 6, 4. Those would be my 6 heights that I'm getting volumes for. Okay, so this is 2, 2, 4, 2, 6, 2, 2, 4, 4, 4, 6, 4. Okay. Now my delta A is 4. And now the function, it's easy, it's just x times y. So I just multiply them. 4, 8, 12, 8, 16, 24. Right? 2 times 2, 4 times 2, 6 times 2, and so on. So multiply it all out, 288. So my estimate, which is probably not very accurate, but my Riemann sum estimate for the volume under this function underneath this square is 288 cubic units. Just like in Calc 1 or Calc 2, you're saying estimate the area under the curve by making rectangles. Okay. All right. Part B says the same thing, except it says to use midpoints. Part B, use the midpoint rule. Okay. So I put a dot on the 6 midpoints. So that looks like what? 1, 1, 3, 1, 5, 1, 1, 3, 3, 3, and 5, 3. So my volume is delta A. Okay. Base this time is area of the base. Area of the base times the vertical height. And all the areas are 4. Right? So it's 4 times f of 1, 1. There's 1, 1. F of 3, 1. F of 5, 1. F of 1, 3. F of 3, 3. F of 5, 3. And again, the function's easy to evaluate because you're just multiplying, just x times y. Right? So multiply them. 4 times 1 is 1. 3 times 1 is 3. 5 times 1 is 5. 1, 3, 5. And then 1 times 3 is 3. 3 times 3 is 9. 5 times 3 is 15. Add them all up, 144. So my estimate by using the midpoints is 144. And by the way, you'll notice the problem's finished, but look at how off these are. They're off by a factor of 2, which kind of makes sense. You don't expect for such a small partition to get answers that are very close. Right? But if I chop this up to 1,000 pieces this way and 1,000 pieces this way, run it through a computer, you'll get a pretty accurate estimate, regardless of whether I pick the midpoint or upper left or lower right or whatever. Right? But here they're not very close at all, just as you would expect. Okay. All right, so that was number 1. I'll let you do number 3. The rest of the time we're doing these double integrals. It's really just a review of integration. So calculate the iterated integral. So 15. So integral of blah, 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 dy, dx. Right. Notice what we're getting here. There's this function, okay, on this rectangle where, let's see. Yeah, question again. When it's like this, look at the way it's constructed. Is y going from 0 to 2 or is x going from 0 to 2? It goes inside out. So y is going from 0 to 2, x is going from 1 to 4. Okay, so you have this rectangular plot where x is going from 1 to 4, y is going from 0 to 2. There's this function above it. I say above, it can be below, right? It's just like when we said area under the curve, that was if the function is positive, but it can be below also. Okay. We're coming up with the net volume of this thing above the XY plane. Okay, the actual integration is straightforward. As you might guess, when you're integrating with respect to one variable, treat the other or others when we get to X, Y, and Z as constant. So when I integrate with respect to Y, treat X as constant for the first part. Okay, so again, it works inside out. So that means you pretend this outside's not even there. Just do this one first. So you're integrating blah, 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 dy. The variable is y, treat x as constant. So what do I do with this? Just copy it. So just copy 1 to 4 and the dx. That doesn't change. Okay, so I integrate So integrate with respect to y. So 6x squared y is 6x squared, it's constant, y squared over 2, which is 3x squared y squared. And the integral of negative 2x, that whole thing's a constant, so it's negative 2xy, right? It's just like saying, what's the integral of 7y with respect to y? So the integral of negative 2x, that's a constant, so negative 2xy. Okay, and now I plug in y goes from 0 to 2. I like to put this down so I don't get mixed up. Technically, you don't have to, but I highly advise it so you don't get mixed up and say, oh, am I plugging in for x or am I plugging for y? And later on, you're plugging in for z also, right? So I like to put down y equals 0. So I go, now, am I plugging in for x or for y? Oh, yeah, I'm plugging in y equals 0. Okay. Now, remember this happened a lot in Calc 1 and Calc 2? A lot of times when you plug in 0, you get 0. Okay, that's going to happen a lot for us. Our integrals are sometimes going to get so long. They'll be so long. If you can see right away that, oh yeah, if I plug in 0, I'm going to get 0, don't even write it down. Okay, so do you agree if you plug in y as 0 right there and right there, it's 0, which means I'm not going to write blah, 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 and then minus 0, minus 0. And you don't have to do that either. Okay, now you might be willing to do it, you know, in Calc 1 when it was just a single variable. But believe me, when you, by the time you get to 2 variables and 3 variables, you really don't want to write down extra stuff if you don't have to. Okay, so don't bother if you know. Now you have to be careful that you are getting 0. Remember, don't automatically assume, oh yeah, 0, it's going to turn out to be 0. Got to be careful because, like, what if it says e to the 0, right? E to the 0 is not 0. E to the 0 is 1. Or cosine 0. Cosine of 0 is 1. Sine of 0 is 0. Tangent of 0 is 0. So be a little bit cautious. But I look and say, okay, if I plug in 0, I get 0. I'm not even going to write it, right? So I just plug in 2 for what letter? Y. So 2 goes there. 2 squared is 4 times 3, 12x squared, minus, put 2 right there, 2 times x times 2, 4x. Okay, and now I integrate with respect to x. Okay, so that's the way the double integrals work. And that's the way triple integrals are going to work too when we start integrating with x, y, and z. Okay, so one more time, it's inside out. So when you see this construction, just kind of cover this up. Don't even look at this. You integrate with respect to y. That means treat x as constant. Okay, so 6x squared is coefficient. Y squared over 2 becomes 3x squared y squared. Negative 2x is a constant, negative 2xy. Plug in for which letter? Y. That's why I'm plugging in the y equals so I don't forget which one is which. Just copy that 1 to 4, copy the dx. Okay, and then this comes out to be 12x squared minus 4x dx. And of course, once you get to this is easy. This is just like Calc 1 and Calc 2 stuff, right? So I don't really have to see much about that. So 12x cubed over 3 or 4x cubed minus 2x squared from 1 to 4, and then I'm pretty much home free. Okay, so 4 times 4 cubed, 4 times 4 times 4 times 4 is 256, minus 2 times 16 is 32, minus parentheses, plug in 1, 4 minus 2, 224 minus 2, 222. Okay, so that's the way it works. Okay. All right, so most of the rest of section 1 is going to be stuff like this. Okay, number 19, we'll start that one. Okay, now they can give me dy dx. And again, from now on, when I say dy dx, it isn't the derivative symbol that looks like dy divided by dx. Dy dx is now the multiplication dy dx. But we can also have dx dy. Later on, we'll have dx dy dz, or dy dz dx, or dz dx dy. There's 6 possibilities there, right? So you just have to be careful which is which. Okay, so when I see this, I do the inside. So forget about the negative 3 and 3, just copy it. Forget about the dy, just copy that. Integrate this stuff with respect to x. That means y is constant. So integral of y is xy. Y squared cosine x, y squared sine x. Okay, x equals 0 to pi over 2. Technically, you don't have to put this down. I advise it. I do it for myself. So, you know, I don't want to get lost. I don't want to accidentally plug in the wrong variable. So that's why I put down x equals 0 pi over 2. Is it true when you plug in 0, you get 0? Yes, sine of 0 is 0. So don't worry about it. So plug in pi over 2 for which letter? X. So pi over 2y plus sine of pi over 2 is 1. So y squared dy. And now this is pretty straightforward. Okay, so pi over 2, y squared over 2 plus y cubed over 3 from -3 to 3. Okay, this becomes 9 pi over 4 plus 3 times 3 times 3 divided by 3 is 9. Minus, okay, if I plug in -3, I get 9 pi over 4. And let's see, you got to be careful. If you plug in -3, -3 cubed is -27, divided by 3 is -9. So the 9 pi over 4's cancel out. I have 9 minus a -9. So the final answer is 18. Okay, so there we go. All right, so these aren't that bad. They can just get really long. It's already long. Wait until we get to triple integrals. You integrate with respect to x, y, and z. So that's even longer, as you can see. All right. Okay, it's getting near 7. So it's a good time to break. Okay, so we'll break. I'll do some more after the break. Maybe sneak in some of section 2, but I'll have to make sure I give you enough time for the quiz also. Okay, we'll break until 7:10. About that, okay? And I'll put that in the chat also. Okay, folks, let's continue on. The quiz will just be on 14.8. Somebody asked about the quiz. So just the Lagrange multiplier section, okay? All right, I'm gonna do more problems in 15.1. I'll probably just introduce 15.2, but not do anything about it. But any little bit that I do today will just help me for next Tuesday. Okay? And a reminder, if you have any questions in preparation for the test, so part of your homework, quote unquote, for Tuesday is if you have any questions, then bring it up. All right, so let me go ahead and share the screen again. If I can get it. Here we go. Okay, so since our exam is here, so next Tuesday, you can ask me questions second half. So part of your quote unquote homework for next time is if you have any pressing issues from 14.1 to 14.8, right? And bring it up on Tuesday because you won't get a chance to ask me anything on Thursday because I'm letting you have the entire class period for the test, okay? All right, so let's go back and do more of these double integrals. So you can see what the problems look like. So we have double integrals, right? Not one, but two integrals. Later on, we'll have triple integrals. And it would say either dx, dy, or dy, dx. So if you see dx first, that means you integrate with respect to x first. And if you see dy first, you do y first. Okay. But again, it works inside out. So when it's written like this, that's dy. These are limits for y. These are limits for x. Okay. So it kind of goes inside out. All right, 23. Integral from 0 to 3, 0 to pi over 2, t squared sine cubed of phi. This is the Greek letter phi. Sometimes it's used for empty set. D phi dt. Okay, and yeah, maybe let me go back and get this out of the way. I'm raising it up for focusing purposes, so you can see a little bit better. If you want to say, if I leave the paper down on the ground like this and say I can't see it too well, so I'm raising it up. I apologize. I know I'm going fast, but you know, you can always pause, slow down the video as much as you want, fast forward, rewind, and so forth. I haven't even covered all these problems yet, but that's okay. Just so you can see it, hopefully. All right, so I hope that was workable. All right, so I'm integrating sine cubed. Remember from Calc 2 how to integrate sine cubed? Write it as sine phi times sine squared, and then change sine squared to 1 minus cosine squared of phi d phi. Right? And then do a u substitution. U equals cosine of phi. Du is negative sine phi d phi. Okay. So the original just had sine phi, so I had to multiply inside and outside by -1. Change the limits of integration. So 0 to pi over 2, that's for phi. And then 0 to 3 is for t. So when phi is 0, u is cosine of 0 is 1. Phi is pi over 2, cosine pi over 2 is 0. So I change the limits of integration. I have a negative outside, 0 to 3. I'm no longer integrating from 0 to pi over 2. I'm now integrating from 1 to 0 of t squared times 1 minus cosine phi squared is now 1 minus u squared. And negative sine phi d phi is du dt. So you can see it gets clumsy when I change variables when I'm doing multiple integrals. So now I'm integrating with respect to u and with respect to t. Okay. And you might recall if I have negative integral from 1 to 0, I can switch it around, make it positive integral from 0 to 1. T squared 1 minus u squared du dt. Okay, so I'm integrating with respect to u. That means t squared is constant. So leave the t squared alone. That's u minus u cubed over 3, right? So integral from 0 to 3, that's for t. T squared u minus u cubed, u equals 0 to 1. Again, I like to put the variable down so I don't get confused. Is it true when you plug in 0, you get 0? Yes, it is. So don't worry about it. Plug in 1, you have 1 minus 1/3, which is 2/3. Factor the 2/3 out. And now, you know, what's a single integral? It's straightforward, right? Integral from 0 to 3 of t squared dt. So 2/3 t cubed over 3 from 0 to 3. 2/3 plug in 3. 3 times 3 times 3 divided by 3 is 9. So 2/3 of 9. Final answer is 6. Okay. Again, what are we getting with these numbers? We're getting volumes. Volume under the function. Here's the function on a rectangle. The rectangle is, for phi, you're going from 0 to pi over 2, and from t, you're going from 0 to 3. And I should say it's the net volume. Now, if this function is completely above the xy plane, it is the volume. Okay. But if any of it is below the xy plane, then it's the net volume, where anything above is considered as positive, anything below is counted as negative. Just like in Calc 1, right? Remember in Calc 1, you have a graph that dips below the x-axis, then the integral is a net volume. You have the part that's above minus the part that's below. Same thing happens here. You could have a graph. Now for this one, I think it's all positive. Let's see, sine between 0 and pi over 2 is all positive, and t is positive. Yeah, so this is the actual volume under the graph. Okay, whatever this thing looks like on this rectangular region from 0 to pi over 2 for phi, this direction, and from 0 to 3 in the t direction, the total volume under that function is 6 units. But again, if part of it's positive and part of it's negative, that means above the xy plane, think of the floor as z equals 0. You could have the graph above, but you could drill underneath and have part of the graph below also, in which case the double integral would be the net volume, right? The part that's above minus the part that's below. Just like in Calc 1, right? Remember in Calc 1, you had situations like this, right? So the integral would be this area minus this area. So just proceed by analogy for volume. Okay, this one is a true volume because the function is always positive, but you could have some that's above the floor and, as it were, drill down below the floor, in which case the integral, the double integral, would be the net volume. Okay. Okay, 29. They don't give you the two iterated integrals, as it were. You make up your own. Okay, double integral over the region R of xy squared over x squared plus 1 dA. So what's dA? A tiny change in area, tiny rectangle. What's this composed of? Well, dx dy or dy dx. 0, 1 cross 3, 3. Okay. It says x is between 0 and 1, number 29. Y is between -3 and 3. It's a little bit more compact to write it like this. So 0, 1, that's for x. Cross, it's not a cross product. It's just a way to write this. X goes from 0 to 1. Y goes from -3 to 3. And if I have another cross, then that will tell me what happens with z. And if I have another cross, that'll tell me what happens with t, the fourth dimension, and so on. So you can set it up either dy dx or dx dy. You have a choice. I decided to go dy dx. So if I'm going dy dx, -3 to 3 has to come first, right? And then 0 to 1. I could also go dx dy. If I go dx dy, then 0 to 1 has to be the inside, because that's going to be for x, and -3 to 3 has to be for y. Okay, now I decided to do y first because that looked like an easier integral, right? That means x over x squared plus 1 is constant, y cubed over 3. right? 0 to 1, -3 to 3. This time I got lazy and didn't put the y equals, but I separated so I knew for sure, okay, I'm plugging in here. I'm not plugging into here. I'm plugging into here. Okay, so if I plug in 3, I get 9 minus, plug in -3, a -9, right? 3 cubed is 27 divided by 3 is 9, minus -3 cubed is -27 divided by 3, -9. That's 18. Okay, so take the 18 out. Integral from 0 to 1 of x over x squared plus 1 dx. Okay, and that looks like a simple u substitution from calc 1 and calc 2. Let u equal x squared plus 1, du equals 2x dx. I don't have a 2, so I put a 2 inside and a half outside. Change the limits of integration. When x is 0, u becomes 1. When x is 1, plug it in, u becomes 2. So I have 1/2 of 18, which is 9 now. The new integral is from 1 to 2. And 2x dx is my du. X squared plus 1 is u. Integral of 1 over u is natural log, absolute value of u. Okay. Plug in 1, you get 0. Natural log of 1 is 0. So final answer, 9 ln 2, as you can see here. Okay. So that's that one. Okay, 33. I hear some background noise. Can somebody please check that everybody please check that you're muted? Okay, 33. Integral over the double integral over the region y e to the negative xy dA 0, 2 cross 0, 3. So what is dA? A tiny change in area. Okay, you can think of dA like this. Here's dx and dy, right? So there's a little plot of land, a dA, and of course it's dx dy, or you can say dy dx, right? Doesn't matter. Okay, and again, let me show you what it says in the book. Oh, this time they actually do the cross notation. Look at 33. 0, 2 cross 0, 3. It's not cross product. It means x goes from 0 to 2, y goes from 0 to 3. All right, this gets a little bit tricky, but I'm opting to go dx dy. And the reason for that is this. It actually becomes a fairly easy integral if you think of the chain rule. Now, look at e to the negative xy. What's the derivative with respect to x? Derivative. You would put e to the negative xy times negative y. I already have a y. See that? And that way I don't have to integrate by parts or anything like that. So the integral is negative e to the negative xy. X goes from 0 to 2. Okay, so this way I had a choice, but sometimes it's much easier one way or the other. Well, maybe one thing to think about, if I integrate with respect to y first, I have to integrate by parts, right? Remember in Calc 2, y e to the y, integration by parts. If I integrate with respect to x, okay, you probably didn't do anything like this before, well, because you didn't have multivariable, okay, but you're thinking backwards of differentiation now, okay, of partial derivatives. If I ask for the derivative of e to the negative xy with respect to x, I'm doing dx, you would put the same thing down and then multiply by negative y. I have a y. So that tells me I want the integral to be negative e to the negative xy. Okay. And if you're not convinced of that, differentiate with respect to x. Okay. You would put the same thing and then multiply by negative y, and there it is. So it works. Okay. All right, and we're integrating from 0 to 2. take a negative out. This time when you plug in 0, you don't get 0. Watch out. Plug in 2 for x, you get e to negative 2y. Plug in 0, you get 1. And the negative's out front. Well, if the negative's out front, I might as well just switch it around, right? The negative of a minus b is b minus a in algebra. So I'm integrating from 0 to 3, 1 minus e to the negative 2y dy. Okay, then I'm pretty much home free. Integral of 1 is y. Integral of negative e to the negative 2y. Okay, did you ever think of this in Calc 2, hopefully, of the chain rule in reverse? Okay, what do I mean by the chain rule in reverse? Okay, a fast way to integrate e to the negative 2y is ask yourself, what do you do if you differentiate e to the negative 2y? You would put e to the negative 2y times negative 2. So how about when you integrate? Divide by negative 2 or multiply by negative a half. So it becomes y plus 1/2 e to the negative 2y. Right? And of course, what answers any question about integrals is to differentiate. Yeah, I messed up again over here. What's the derivative of this thing with respect to y? Oh, well, yeah, the only letter is y, so didn't have to worry about that. That's 1. The derivative of this is the same thing times negative 2 by the chain rule. Well, negative 2 times positive 1/2 gives me negative e to 2, so it definitely works. All right, plug in 3. 3 plus 1/2 e to the negative 6 minus, plug in 0, that's 0, but that becomes 1/2. Right, 1/2 times e to the 0, 1. So 3 minus 1/2. Final answer is 5/2 minus 1/2 e to the negative 6. Okay. All right, let's see. 35. You had to draw a little bit. Sketch the solid whose volume is given by the integrated integral. So you didn't have to actually evaluate it. If you evaluate, you would get the volume. But how do you graph that thing? Okay, very carefully. Okay, so 0 to 1, 0 to 1, 4 minus x minus 2y dx dy. Okay, first of all, you should recognize that this is a plane. Z equals 4 minus x minus 2y indicates a plane. Okay, so the easiest way to do that, you've got nice, regions, just 0 to 1. Okay. All right, so what I did was I just plugged in the corner points. Okay, so 0, 0, 0, 1, 1, 0, 1, 1. Okay, so f of 0, 0 is 4, right? F of 1, 0, put a 1 here and a 0 here, you get 3. F of 0, 1 is 2. Put a 0 here and a 1 here, get 2. And f of 1, 1, put a 1 here and a 1 here, you get 1. So those are the heights. So all I did is try to plot those 4 points and then connect them with a straight line. Okay, so at the origin, I went up 1, 2, 3, 4 units. 1, 0 is over here, right? 1 unit out. I go 3 units, and yeah, you can't be careful. You're creating the illusion. I don't put it as high as this. See, this is 3. Yeah, but remember, you're walking out 1 unit. So, and you artists know this better than I do. But if you're coming out 1 unit here, you would take this as 3 and draw a parallel to this thing, and that's going to be considered 3 units, right? So this vertical distance matches this vertical distance, which is supposed to be 3. So from a perspective standpoint, you're not supposed to go up to here because coming out this way is supposed to be considered straight, right? But I do want this vertical distance to match this vertical distance. Okay, so that's considered 3 units up. Right, and of course you artists know this better than I do. There's actually a lot of good math in art, but yeah, that's beside the point. Okay, f of 0, 1 is 2. This one I can actually go straight up because that is in the YZ plane. Right, so if I go 2 up there, I can just go 2 up there. So that's 0, 1, 2. And then f of 1, 1 is 1. This is the one, again, I have to create the illusion of going up 1 unit. Okay, so I take this distance and I match that from over here. I don't make it as high as this, right? If I go straight up from here and make it as high as this, it's actually going to look like it's more than 1 unit, right? For you artists perspective thing, this vertical distance has to match this vertical distance. So that's considered the point 1, 1, 1. Okay. All right, and then I just connect them, and that is going to be the plane. It's kind of a weird looking thing. Can you imagine if you're at these 4 corners, right? They all have different heights. Okay, so imagine a room. Now we don't see rooms like this usually, right? Usually when we have rooms in your home, it's the same distance, straight up everywhere you go. This weird building, I suppose, if you're standing here, the height is 4. If you're standing here, the height is 3. If you're standing here, the height is 2. And if you're standing here, the height is 1. So it's kind of weird, right? The total volume, well, do this double integral, and that'll give you the volume, right? Okay, and let's see. What else did I want to show you? Um, $37. Find the volume of the solid that lies under the plane 4x plus 6y minus 2z plus 15 equals 0, and above the rectangle xy goes -1 to 2 and -1 to 1. Okay. So what you want to do is solve for z. Okay. So when you're integrating, you're basically integrating z, just like in Calc 1 and 2, you were integrating y. Remember, you were integrating f of x dx? You were really integrating y, which was the height. So in this case, which, yes, I messed up again. Okay, you solve for z, and you're integrating z, which is the height. So again, that's the reason why now, back on day 1, we wondered, why are we letting z be this way? Why don't I just leave x and y the way they are and let z be the oddball out? Okay, and the reason is, as we can see now, we want z to be considered the height. So we're integrating z, which is f of x, y. Just like in Calc 1 and 2, when you integrated f of x, you're integrating y. You're integrating the heights. Okay, so a little bit of simple algebra. Z is 4x plus 6y plus 15 divided by 2. And that's what I was trying to integrate here until I messed up. So I come back over here. All right, so I took out the half. So I just had to go dx, dy. You can go dy, dx. So -1 to 1, -1 to 2, 4x plus 6y plus 15. Remember, it was supposed to be divided by 2. I don't want to carry the fraction out, so I'll just take 1/2 of the whole thing. You can also go dy dx. If you go dy dx, then these limits would be switched, right? Then -1 to 2 would be outside, and -1 to 1 would be inside. Okay, this is a rectangle, right? In the xy plane, okay, you're going from -1 to 1 in the x direction and -1 to 2 in the y direction, and you've got this graph above it. We're finding the volume. Okay, very powerful. Just like in Calc 1 when you were doing area under the curve. We're now doing volume under the function. Okay, integrate with respect to x. That means y is constant. 2x squared. 6y means 6y is constant, so 6xy plus 15x. From -1 to 2. And unfortunately, this time, I don't get to plug in 0. So I plug in 2, 8 plus 6y plus 30. I don't like that. 6 times 2 is 12. Looks like I messed up again, folks, which is nothing new, as you know by now. So somehow I got the right answer. So this might be a case of 2 wrongs make a right. Well, let me just give you the theory at least. It looks like I goofed again, but you know, that's par for the course for me, I guess. But if I did this correctly, which evidently I didn't, sorry. But you plug in 2 here and here and here. Let's just go with what I have. 8 plus 6y, it looks like it's gonna be 12y, plus 30, minus parentheses, plug in -1, 2 minus 6y minus 15. From -1 to 1. Okay. And let's see. I'm not sure what I got after that. Okay, I ended up with 51, which I think is a combination of 8, 30, and 15. And a minus 2. Okay, and then complying all the y's, 6y minus a minus 6y, 12y. So assuming I didn't goof there, 51 plus 12y. All right, so 51y plus 6y squared from -1 to 1. So I have 1/2 of 51 plus 6 minus -51 plus 6. 6 cancels out. I have 1/2 of 51 plus 51, which is 51. Okay, but I'm starting to doubt whether I did that correctly, but anyway, that's what that's about. Okay, well, at least you got the idea. Okay, one more like that, and then I'm done for this section. See, which one did I want to show you? Yeah, 41. Find the volume of the solid enclosed by the surface z equals 1 plus x squared y e to the y, and the plane z equals 0. That's the xy plane. X is plus or minus 1, y equals 0, y equals 1. So I'm integrating for x from -1 to 1, y from 0 to 1. Okay. All right. So this is a function that you integrate. All right. Looks like I decided to go for dx first. Looks like it was easier. So -1 to 1 for x, 0 to 1 for y. If I did dy first and then dx, of course, you would be 0 to 1 inside, because that's y, and -1 to 1 for x. All right, so if I integrate with respect to x first, then y is constant. That means y e to the y is all constant. So x plus 1/3 x cubed y e to the y from -1 to 1. Okay, so if I plug in 1 for x, I get 1 plus 1/3 y e to the y minus -1, put -1 there, -1/3 y e to the y. I have 1 minus a minus 1 is 2. 1/3 minus a minus 1/3 is 2/3 y e to the y dy. Okay, now I had to do a little timeout to do the integral of y e to the y. That was integration by parts. Do you remember integration by parts? Calc 2. So a little timeout here. What's the integral of y e to the y? So u equals y, dv equals e to the y dy. Remember doing that in Calc 2? du equals dy, v equals e to the y. So the integral formula was uv minus the integral of v du. So u times v, y e to the y, minus the integral of v du, e to the y dy. But the integral of e to the y is just e to the y. So you get y e to the y minus e to the y plus c. Okay, so the integral of y e to the y is that. So I put that way back over here now. Okay, so back to integrating this thing. So I have 2y plus 2/3 integral of y e to the y, which I now know to be this. So 2y plus 2/3 y e to the y minus e to the y from 0 to 1. Okay, plug in 1, I get 2. Notice if you plug in 1 right here, this becomes 0, doesn't it? It's e to the y minus e to the y. Put a 1 right there. So it's 2 plus nothing, minus plug in 0, that's 0, that's 0, that's e to the 0, which is 1. So it's 2/3 times -1, which is -2/3. So it's 2 plus 2/3. Final answer is 8/3. And there we go. Okay. All right, so I'm done with the section, folks, and that was all I was going to give you. I'm going to introduce the next section, show you where we're headed, and then I'll start lecturing on it on Tuesday. So I'm officially finished with 15.1. I'm going to mark it off so you can verify that. Okay, what is 15.2? It's a much richer variety in multivariable. Double integrals over general regions. So section 1, we just integrated over rectangles. Stuff that looks like that. Okay. Or you can even see the title of the section, double integrals over rectangles. Okay. All of these are rectangular regions. X goes from something to something. Y goes from something to something. Those are constants. You get a rectangle. But we have a much richer variety now. Suppose we want to integrate over figure 1, figure 2. So look at that. We want to find volume under that region. Okay. Much more rich possibilities in multivariable. That once you see that, you think that Calc 1, it's so ordinary now, right? All you do is integrate from A to B along an interval, right? Which is just a subset of R, the real number line, right? Okay, I'm integrating from A to B. Now it's almost like you're saying, is that all? All you can do is integrate from A to B. Well, now in multivariable, you could integrate over a rectangle, but you can integrate over something that looks like that, right? You can integrate over circles or funny things that look like that, or like that, or like that, or like that. Okay. Or that, or that. Okay. And we never got a chance to do that in Calc 1 and Calc 2 even. It's fairly ordinary. And now it's almost like, is that all? If that's all you're doing, you're only integrating from 3 to 10, right? That's the only choice you had. Okay. Now a whole new world of possibilities opens up. You can integrate over regions like this. And of course, once you get to 3 dimensions, you can integrate over spheres and rectangular boxes and, you know, ellipsoids and hyperbolic paraboloids or whatever. You can integrate over anything that you feel like in 3 space. Okay, so that's what's going to be happening. We might integrate over regions that look like that, 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 that. Okay, so what are they doing? Okay, and what are the arrows? Suppose this is the region that you're trying to integrate. There's function only above this. Okay. So maybe this is a plot of land. Maybe your home is in this weird shape and it has certain heights based on this. And you're trying to find the volume of my home that happens to look like that, or my building that looks like that. Okay. The arrows like this means you're integrating with respect to what? Y first and then X. Here, X first and then Y. Okay, so you might have a choice. One way might be better than the other. It depends on the functions and it depends on the shapes. Okay, I'm just showing you over here. you could integrate this way. So this would be upper and lower. So if I'm integrating with respect to, I know what I'll do. Figure 9, page 1003. Here's the region that I'm trying to integrate over. Y equals 2x and y equals x squared, bounded by that region. This way means integrate with respect to y first. Upper, lower. Upper function is 2x, bottom function is x squared, right? Remember in Calc 2, right, you had to determine which is the upper function, which is the lower function. You could go this way where x is a function of y. That means you have to write each of these as x is a function of y. You did some of that in Calc 2, right? So you would write this as what? X equals half y, x equals square root of y. There it is, right? X is a function of y. Now the upper function would be the parabola and the bottom function would be the line, because if you're going this way, right? Upper means further to the right. Lower means further to the left. And I guess if you turn the book 90 degrees, can't really show it to you very well, but you can see, right? Then you see, oh yeah, this is the upper now. Upper meaning further right, further left. In which case you have to write them both as x is a function of y. So sometimes it's better to go this way. That's essentially what's happening in the next section. Rather than just rectangular regions, you could have all kinds of shapes, triangular regions. Okay. What's happening here is they're trying to show you going this way is not as good as going this way. Because going this way, you have to split into two pieces, upper, lower, but the lower changes through the problem, right? The lower function is this piece, and then when I go over here, the lower becomes this one. If I switch to x as a function of y, that's advantageous in that there's just one function. The line is the upper, the parabola is the lower, so you can just do that all the way through. In which case you want to integrate x as a function of y first, as y goes from something to something. Okay, so it's a much more rich variety of problems that we have in section 2, and that's the basic idea behind section 2. Okay, but otherwise I'm done. So I'll take any quick questions if you have any. If not, I'll give you the quiz and then we'll call it a night. Okay. So any questions anybody want to ask? Otherwise, we'll go straight to the quiz and that's it. All right. Yeah, somebody had a question? No? All right, quiz time. Get your cell phones out or be ready to do a screenshot. I hope you'll find it's not too bad. Section 8, Lagrange multipliers. Find the maximum and minimum values of f of xy equals 3x plus y, subject to the constraint x squared plus y squared equals 10. Okay, it should not be that bad, in my opinion. Of course, when I say it's easy, you know, people don't believe me because I'm the teacher, right? So, oh, you know, everything's easy for me. But I think it's not that bad for students. Okay, find the maximum and minimum values of f of xy is 3x plus y, subject to x squared plus y squared equals 10. Do the method of section 8, Lagrange multipliers. I'll hold this up for another 10, 15 seconds. Go ahead and get started. But I'll set up your breakout rooms. Again, put your first and last name of everybody in your group. As usual, if you finish early, you can leave. Make sure after you finish, get everybody else in your group to get it. I'll look at all of them, but I only grade 1. So in order to be sure to get it right, make sure everybody in your group has it right. And then it doesn't matter who I grade, right? Then you all get full credit. All right, I will assume that you all have it now. So I'll make this disappear. Go ahead and get started with it. I will stop the recording.